Before we go any further, let's be precise about what actually happened here, because the real story doesn't need any exaggeration to be alarming. There is no single terrifying announcement from 3 minutes ago. What's real is this: over a span of about 2 weeks, in late March and early April of 2026, 2 separate pieces of research quietly landed. One from Google, one from a smaller quantum computing startup, and together they did something cybersecurity experts have been dreading for years. They took the date on which quantum computers could plausibly break the encryption protecting the entire internet and moved it dramatically closer. Close enough that Cloudflare, one of the companies quietly securing a massive share of global internet traffic, publicly announced it was accelerating its own security deadline in direct response. This is the real story of what Google's quantum AI division actually confirmed, and why cybersecurity professionals are treating it as a genuine turning point rather than just another research headline. To understand why this matters, you first need to understand what almost the entire internet currently relies on to stay secure. Nearly every private conversation, every online purchase, every login, every piece of cryptocurrency, and every secure connection between your device and a website depends on a category of mathematics called public key cryptography. It works by relying on math problems that are, with current computers, essentially impossible to solve in any reasonable amount of time. Things like factoring extremely large numbers, or solving what's called the elliptic curve discrete logarithm problem, the specific mathematical foundation behind a widely used encryption standard called ECDSA, which secures a huge share of ordinary web traffic and underpins the security of major cryptocurrencies like Bitcoin. As long as solving these problems requires more computing time than exists in the history of the universe, the encryption built on top of them stays safe. Quantum computers threaten that entire foundation, because unlike ordinary computers, they're theoretically capable of solving exactly these kinds of problems dramatically faster, using specialized quantum algorithms developed decades ago in pure theory, long before any hardware existed, capable of actually running them. The moment when a quantum computer becomes powerful enough to actually break real-world encryption has a name in the cybersecurity industry: Q-Day. For most of the past decade, most serious estimates placed Q-Day somewhere out in the mid-2030s, comfortably distant, giving companies and governments time to gradually transition toward newer, quantum-resistant encryption methods before the threat became real. That comfortable distance just got a lot shorter, and here's exactly why. On March 30th, 2026, Google's quantum AI division released a white paper containing a specific, formally demonstrated result. They had found a way to solve the elliptic curve cryptography problem, the one underpinning ECDSA and Bitcoin's own security, using roughly 20 times fewer computational resources than researchers had previously believed necessary. According to Google's own published estimate, this improvement suggests that fewer than 1,200 logical qubits, the error-corrected, highly stable version of a quantum bit that current hardware still struggles to produce reliably, could theoretically be enough to solve Bitcoin's specific 256-bit elliptic curve problem. On the kind of superconducting quantum hardware Google itself has been building for years, that estimate translates to roughly under 500,000 physical qubits, a genuinely massive machine by current standards, but for the first time, a number that sits within a plausible engineering roadmap rather than pure science fiction. It's worth being precise about exactly what Google actually released, because it matters for how seriously to take this. The company did not publish the actual working algorithm itself. What they published was a formal mathematically verified proof that such an algorithm exists and performs exactly as described, without handing over the specific blueprint, a deliberate choice reflecting how seriously the implications of this particular kind of research are now being treated inside the field. Then, within roughly the same window of days, a separate announcement landed that made the picture even more concerning. Researchers connected to a startup called Oratomic, working alongside a Caltech research team, published a resource estimate specifically focused on a different, still enormously important target, RSA 2048, and a related standard called P256, two of the most widely deployed encryption methods securing everyday internet traffic, banking systems, and countless pieces of critical digital infrastructure worldwide. Their estimate focused specifically on a newer style of quantum hardware called a neutral atom quantum computer, rather than the superconducting approach Google has traditionally used, suggested that breaking these encryption standards might require as few as 10,000 qubits. Researchers across the field describe that number as shockingly low, dramatically below what most previous serious estimates had suggested was necessary. Individually, either one of these results would have been a significant piece of quantum computing news. Together, arriving within roughly the same 2-week span, they represented something that genuinely startled people whose entire job is securing the internet. Bas Westerbaum, a cybersecurity researcher at Cloudflare, one of the largest infrastructure companies protecting web traffic globally, told reporters plainly that it was a real shock and that the industry would need to speed up its efforts considerably. That wasn't hyperbole from a headline writer. It was the direct, on-record assessment of someone whose entire professional life revolves around defending internet infrastructure against exactly this kind of threat. Cloudflare's response came fast. On April 7, 2026, just days after both pieces of research became public, the company officially announced it was accelerating its post-quantum security roadmap, setting a new target of 2029, years earlier than most previous industry planning, to make its entire platform fully resistant to quantum-based attacks, including the much harder challenge of quantum-resistant authentication, not just encryption. To understand why that distinction matters, it helps to understand that the cybersecurity industry has actually been preparing for quantum threats for a while already, but mostly focused on one specific kind of attack, something called harvest now, decrypt later, where an adversary today simply collects and stores massive amounts of currently encrypted data, patiently waiting for a future quantum computer capable of decrypting it retroactively. Cloudflare has already made real progress on that front, with over 65% of the human traffic flowing through its network now using post-quantum encryption. But these new breakthroughs shifted urgent attention toward a scarier, more immediate category of risk: authentication. As Cloudflare's senior product director Sharon Goldberg explained, if a quantum computer becomes capable enough to forge legitimate authentication credentials in real time, an attacker wouldn't just be reading old stolen data. They could actively log into systems they have no business accessing, impersonate legitimate software updates, or compromise the digital certificates that verify a website or piece of software is genuinely who it claims to be, all happening live, in the moment, rather than years after the fact. Google didn't stop at publishing research either. The company adopted the same accelerated 2029 target for its own internal post-quantum migration, and has already begun deploying post-quantum protections across major products including Chrome, Android, and Google Cloud, while reportedly pushing other internal engineering teams to follow the same aggressive timeline. IBM, another major player in this space, has stated publicly through its Quantum Safe division that it hasn't ruled out the possibility of a genuine large-scale quantum attack becoming possible as early as that same 2029 target, with the company's own roadmap aiming to deliver its first fault-tolerant quantum computer, a machine called Starling, by that same year. Now, here's where it's important to stay grounded in exactly what has and hasn't actually happened, because overstating this helps nobody, and the real accurate version is concerning enough on its own. No quantum computer capable of actually breaking real-world encryption exists today. Not at Google, not anywhere else in the world. What changed in March and April of 2026 wasn't a machine suddenly appearing that could crack your bank account's encryption overnight. What changed was the theoretical and engineering roadmap, the calculated distance between where quantum hardware currently stands and the point where it becomes genuinely dangerous to modern cryptography, shrinking substantially and unexpectedly based on real, published, peer-reviewed mathematical improvements rather than speculation. Building an actual machine with the hundreds of thousands or even tens of thousands of stable, error-corrected qubits these estimates describe remains an enormous unsolved engineering challenge, one that still requires major breakthroughs in hardware stability, error correction, and manufacturing that nobody has fully solved yet. But the direction of travel matters enormously, and that's exactly what has genuinely alarmed serious cybersecurity professionals rather than casual observers. For years, the consistent, comfortable assumption across the industry was that Q-Day sets safely out in the mid-2030s, giving organizations plenty of runway to gradually transition their systems. These two announcements, landing within days of each other, from a major technology company and an independent research team working through entirely different approaches, both pointed toward the same uncomfortable conclusion. The actual computational resources required to break the encryption protecting the modern internet may be dramatically smaller than almost anyone in the field had been planning around. And multiple major organizations, not just Google and Cloudflare, but IBM and others across the industry, responded within days by formally, publicly moving their own internal deadlines years earlier than previously planned. That's the real story. Not a single terrifying image, and not a machine that suddenly, secretly broke the internet's security overnight. Something quieter, and in its own way more unsettling. Two pieces of careful, peer-reviewed mathematical research, released within roughly 2 weeks of each other, that collectively convinced some of the most security-conscious organizations on the planet that the safety margin they'd been counting on had just gotten meaningfully smaller, and that the work of actually protecting the systems billions of people rely on every single day needed to speed up, starting immediately, rather than sometime in the comfortably distant future. If stories like this, the ones where the real, carefully documented research turns out to matter more than any exaggerated headline built around it, are what you come here for, stay close, because the race to secure what comes next is only just getting started.